Okay. Hello, everyone. So, in this lecture, we're going to continue our learning for the value function approximation methods. Okay. So, outline for today. So, previously, we have been learning this on-policy prediction with approximation. We are using different ways to approximate on-policy prediction methods. So we learned some the Monte Carlo on-policy Monte Carlo prediction. Yeah, it's a parameterized, right? We use the weight to represent the states. Okay, linear combination. So in this lecture, we're gonna continue learning this knowledge. Especially, we're gonna learn how we can build the feature, which is here, feature construction. Okay, feature construction. How we can use the linear method to compute features. And in the linear method, there could be several basis functions. We're gonna learn those functions. And after that, we're gonna learn how we can approximate the prediction or value function from a linear function with the neural networks. Okay. So first of all, we are using this RL framework to explain what we are doing. So basically, we have this agent and the environment. So the agent has a policy, which pi as. So you give a state, then it will generate an action, which is called policy pi. Then we usually have two functions: state value function and action value function. Each of them is represented by the VSW, QSAW. Now we are updating our RL framework with parameterized value functions. So previously we just used S. Now we have a W, which is a weight matrix or weight vector, similarly to the action value function, SAW. So we are using weight vectors or matrix to represent the state. Then if we want to do the prediction, we can just update the state value function. If we want to do the prediction, we're gonna use the Q function. And so the one major difference is that we are introducing the new parameter here. Okay, so the value function and the state value function and action value function are parameterized by the weight. Actually, this is from the previous what we learned: unstep bootstrapping and planning with the learning. Okay, I will not cover it. So especially I will briefly cover what we learned in the last lecture. So issues with the tabular method, we have learned the tabular methods in the past several weeks. So but the thing is for those tabular methods, if the state space is huge, then it's difficult to represent the states, right? And also we may have some unobservable states. It may be difficult to find the optimal policy within the limited time and data. Yeah. So then how we can generalize a way to learn those states? Actually, there are multiple ways, right? So previously we have this tabular, and we can also use a linear function. As an example, we use this grid like XY coordinates of XY to represent the state value, right? We use this linear combination of XY and with weight W1 and W2 to represent the value of the state. So these XY are considered as the features for this a particular setting, a problem. But we can also have a nonlinear function to estimate the state values or to do the prediction, to choose an action. So the weights are these links among the units or nodes in the neural networks. So the input are the features. They can be different features into the like one or two layers neural networks. Then we do the deep learning to update the weights, right? So we're gonna learn this today. We just recap what we learned. Prediction with approximation. So now we are parameterize a function with a weight vector. So previously we only have a vs. Now we have a v hat as w. W is the vector, okay? Then to approximate the target, the state value. So for example, here this w can be the linear combination of a feature space, okay, which is x, y. So now we can rewrite what we learned in the past, in the first half of semester, like Monte Carlo method, TD0, n-step TD, and DP. We can rewrite the update process. For Monte Carlo, we can update. So so we consider each episode. So at the end of episode, we update the state value with the return. So in that case, actually, similarly, we can use W. So inside GT, there is a W. So it didn't show here. For TD0, so we are showing here, instead of directly use the state value, we are parameterized, okay? Similar others. But the thing is, we can use this function approximation using by those linear combination or parameterized way. But the thing is, the supervised machine learning method assumes a static training set, which is different from what we are doing in reinforcement learning. And also, so reinforcement learning requires online learning. So supervised machine learning in our case, we need to deal with incremental acquired data. So in supervised machine learning method, they just assume that all the data is already available. We can just directly use the data to do the training. Then I also need to learn non-stationary target functions. Sometimes we also need to have a bootstrapping. So this right-hand side is the kind of showing one limitation of the linear function. For example, if we have this situation, we have this circle state value. Actually, we cannot use the linear function to represent the state values, okay? So, I mean, we just cannot find the weight W1 and W2 to represent this kind of situation. Because X, Y will be represented by the index or coordinates 1 to 5, 1 to 5. So, for example, here, for this case, use 2 and 2, then probably weight will be W5 and so now you can just put into the 2 and 2 and find the W1, W2. There could be some values to align with this 10, but if you move to here is 0, then 0 means that X, Y are not 0. So it means that W1 and W2 need to be 0. But obviously it's kind of difficult to align the two state value with only these two weights, right? So this is a limitation. So then as another example, so we are using, so for example, we are using this linear function, W1 and W2 as the parameter, and X, Y are the features. So we use this index or the coordinates to represent the state values. For example, we use W1 equals 3, W2 equals 5. Then we can generate how we can calculate. We just use this linear function to calculate the state values, then 3 and 5, right? Similar to here. So if we change the weight, so all the state value has been changed. So actually, it is possible that some state value may have a be changed in a different way, okay, instead of following this linear function. So now we need objective for predicting the state value. So we assume that, so here we have several assumptions or precondition to build this objective. The first condition is that we assume that the number of states is greater than the number of weights. So because one of the reason we are that we are introducing this approximation methods is that if the state space is huge, right? It's so we cannot just approximate or calculate the state values. So here we put this: the number of states is greater than the number of weights. Okay, so in this way we can reduce the calculation and the representation space for the number of states, right? Some state value may get accurate, others may not. So this is a limitation I just mentioned in the previous slides here. So if we change the weights, then some state values may be better, some state value may be worse. So that's why we need a state distribution. We use mu s to represent that, which is which to indicate that the importance of state to get to an agent. So it's like following a distribution to represent. So the S, so each state has some like importance, whether it's frequent visited states or less frequent visited states. Yeah. So in this case, actually, we can sacrifice some states, but put higher priority on other states that are important to us. So then we define this mean squared value error, denoted the VE bar. The VE bar W is defined as so we use this mu s times for the importance, right? Because this is the probability. So we just actually you just use the mean squared error, the term, to represent the error. So we want to minimize, right, this error, so that then we can keep updating this W. It gives the rough measure of the error between the estimate and the true value. The mu s shall be the fraction of time spent in the state S. So it also called on-policy distribution, a stationary distribution under pi. So yeah, so this need to be like the fraction of the time spent in the state S. So mostly the starting, since we are considering these reinforcement learning problems, so mostly the starting state is the state the most visited, right? So yeah. Then to minimize this VE bar, actually we rely on this stochastic gradient descent, the approach to like reduce this to approximate, to reduce the error of the weight by updating these weights, right? So as I mentioned, we already learned this W1. So we have this weight vector. Then remember, actually we use the transpose here to represent, actually it should be a column. Yeah. So the state value Vs is differentiable. So there's several conditions, because for using SGD, there are several conditions. Okay. The differentiable, because it should need to be continuous. We can update WT at each time step. And so every time we do the derivative, right, at each step, a new observed state ST is obtained. And so the reason we call it in RL framework, we call it stochastic, is that these the next state may or may not be the successful state of previous state, right? Because it can be considered as a stochastic. Yeah, like, for example, the from one state to another state, actually, yeah, it can be the random state. So example of using SGD, then normally, so we want to update this WT gradually. So this JW is the objective function, Okay, in our case, we will define this later in the next slide. So ideally, we want to find the local or global minima points. So there are some points we need to avoid to approach local maximum standard points. Okay, and the alpha is a step size to adjust the speed. And this is the one hyperparameter to adjust. Okay, so based on this update equation, we can define this update process in the RL environment. So by SGD, we adjust the weight vector after each step by a small amount in the direction that would most reduce the error, which is the gradient, right? So how we define this? We just put the VE bar, the inside of the squared error inside of VE bar. So we put to here, then we do the gradient, right? To the WT, we do the gradient. So if you calculate this we do the gradient with respect WT, then we can get this form. So remember, this is a minus. So inside of this, there's a minus. That's why there's a become positive. Then eventually, if we rearrange the here, so eventually this one is extracted out because and the 2 is cancelled here, right? So the alpha is a positive step size parameter, should decrease along the time. So the alpha is the speed, the learning speed, right? So initially it can be large, but later it will be reduced step, to avoid the less optimal solution, right? Then this delta FW, this is not delta, this is nabna. Nabna FW denotes the column vector or partial derivative of FW. So which is here, right? We use this nabna to do the partial derivative with respect to W, the vector W, to each element, right? So if you look at this figure, derivatives of FW. So if FW become positive, actually it's moving towards the right hand side. If it become negative, it's moving towards the left hand side. So our goal is to move this partial derivative to the local or global minimum points. So for example, if we consider this value function, parameterized value function, as a linear function means that each feature is kind of is a linear combination of each feature. So each feature has a weight, has a coefficient, and we just sum them together. They become a linear function. So if we do the partial derivative with respect to the Wi, then we just directly get the xis, because if you see here, to each component, then xis become the number, the scalar number. The Wi is a variable, right? So if you do the partial derivative, then immediately we get xis. So we can rewrite this the gradient of v hat sw equals xs. So they are the vector. Then we go back to this previous function, what is that? Minimizing function. Okay, so we want to minimize the error, update the w, the weight vector. So the thing is, in this, if we want to use this process, one issue is that this v pi st is unknown because we don't know the environment. So it's a target value, this optimal value we want to learn, right? But at the moment we don't know. Okay, so Yeah, then we can change the version of SGD to a estimated version. So we can replace this V pi st with an estimate. We use UT to represent this estimate. Now this SGD process is it's replaced with this form. So previously it was V pi st, now it becomes UT. Okay, then UT, if UT is an unbiased estimate of V pi st, so means that, so if we just do the expectation, calculate expectation means the average, so it eventually will equal to the target, the seed values, right? Then WT is guaranteed to be converged to a local optima. Then if you recall the Monte Carlo target, actually the Monte Carlo target is unbiased estimate for the target state value, because we are updating the state value based on many episodes. At the end of episode, we update the state values. Actually, those information, the state value we are updating based on the real world, the real target, the data, right? So there's no bias, even though it's slow, but it's not biased. So in this case, we are having the first algorithm, which is the gradient Monte Carlo algorithm. Okay, so I will not go to detail. Actually the overall process is similar. We add a gradient, means that this process is based on the parameterized value function updates. Okay, so the initialized value function weights W arbitrarily, like 0. So similar to the Monte Carlo process, loop for each episode, generate the sequence, and loop for so based on this sequence, then we can, at the end of the sequence, we can update the state for each the state value. But so the GT is a return, right? So we can calculate, then with this WT, we can update this W. So yeah, this yeah, as we mentioned, depends on this the parameterized function, feature function. Actually, we can have a different process, different calculation process. Semi-gradient, if we use the TD or others like a biased update process, it become a semi-gradient method. Okay, we call them semi-gradient method because we are using the changing WT. So it's like we are using estimate value to update the previous estimate value. Okay. So there are several merits here. So based on the semi-gradient TD0, then we can, by using this TD0 update, we just replace here this SGD equation. So others are, if you remember TD0, the one-step TD, right? So the overall are the same process. So for each episode, loops through each step of episode because it's a TD0, so we need to loop through each step. So we need to update. We choose an action from the policy pi, take an action, observe the reward, move to the new state. So with this information, we have a current state, action, reward, and new state, right? So we have a previous state, reward, new state. Then with this information, we can update this weight vector. Okay. So state aggregation, because since we are considering the large state space, so sometimes we may group states together for updating instead of treating each states individually. They may save some like memory or speed up this learning process. Okay. So as I mentioned, that we can just group some states together as they use the same value. Okay. And so in the last lecture, actually, I showed you how we can calculate this based on this random walk. So just a little bit like refresh here. Okay, so we have this random walk. So this is the previous setting. We have this random walk. You always start from here, and you have left hand side, right hand side. They are all terminal states. So you only have a positive 1 reward when you reach to the right hand side terminal state. In other state, you will just get 0. But in our case, so we are updating this process a little bit. Now, instead of this, we only have previously we only have 5 states. Now we have 1,000 states. So you can consider that we have 1,000 states among them. Then similarly, we have left terminal state, right terminal state. And another change is that, so once you start from you are staying in one state, you can either jump to left or right neighboring states, 100 neighbor states, one of them, okay? So you can visit one of the 100 neighbor states, either left or right, okay? So this is one difference. So it means that if you are in the state C, you can choose jump to the left states as long as it is within 100 neighbors, okay, one of them, or right-hand side, the 100 neighbors, one of them, can jump them. Then in this setting, then we can, since this is, you can group each 100 state, we can group them together. So W1 to W10. So now we are, so each 100 states will share 1 weight. So we totally have 10 weights in a vector. So we use this gradient MC algorithm to update this the weight vector here. So if we use a linear function like this format we designed, right? And with the one hot vector, this one hot vector is to indicate which state, which like group the state is lying in, okay? For example, here, if for the initial state, like 0, so here we are using starting from 1. So 1, 2, 3, 4, 5. Actually, this W5 is a starting point, which is 1, okay? Then others are 0. So because the S500, the starting states will be here, right? Now the gradient of this we had SW equals XS. And we used this update. So in the last lecture, I showed you how you can calculate this weight update, right? The first step, you can step by step to update this. So each time W is a vector, you need to write down the vector. Then the XS already we XS just the state is a feature, right? So since just linear, it's just the state itself. Okay. So I will not go too detail about this. You can review the previous lecture, the recorded lecture. So if you run this process, so here we just give one episode. If you run like, for example, 100,000 episodes, then you can update. Eventually, we will approximate to this true value of V pi. Since we are grouping, so you see this like step, like rectangle, this like function. So because every 100 states are grouped together, they share one state value. So, but eventually it kind of converged to this true value. Okay. Okay. Linear method for FGD. So now a linear function's gradient is this. If it is a linear function, then we do the gradient, it will just equals the XS itself. So we use this So this estimated version, okay, so alpha ut, this is ut. If it's a TD0, then it become become this. We can just put the information here. You will see the details and rearrange the order. So this is for this, calculating the TD fixed point. So eventually, we can analytically calculate the convergent point. So as you can see here. So if we use TD0, semi-gradient TD0 approximation approach, then we can eventually get this step functions, which a little bit deviate from the true value due to this TD method itself is a bias, right? N-step semi-gradient TD. So the N-step TD, but in this time we are using the parameterized update process. And it's a performance summary. Okay, we spent this time to review what we learned in the last lecture. Now we are moving to the new content. So the thing is how we can construct the features for linear method. Actually, there are several methods: polynomials, Fourier basis, or Coarse coding. Okay, and we also gonna learn how we can select this step size manually. Eventually, we will reach to this nonlinear function approximation. Okay. The first thing is feature construction for linear methods. So previously we are learning this. We parameterized the value functions, right? Set value functions. In there actually there is a if we look it back, okay, from here. So we define the state values as in this way, and the W. So we define this mean squared value error. Then we design the SGD method to approximate this to update this weight, right? We use a different target to update weight. If we use the linear function as the approximation function, then actually this linear function can have a different basis function to be used. So linear methods has some merits here. Convergence is guaranteed, efficient in both data and computation, but it has some limitation. But the above two merits depends on state representation, which means how we can do the feature selection. So choosing features better is a way to add prior domain knowledge for this learning process. For example, if our target reinforcement learning environment is a geometric object like shape, color, size, or function. If we consider a mobile robot, then we usually consider the location, battery power, sensor readings, and so on. So for those different kind of features, we can add them into these linear methods. But one limitation of the linear method is that there could be no interaction between features. So let's take a look at the example. This pole balancing task example. So assume that you have this cart and you have a pole. Our goal is to keep this pole standing upright while moving the car. So the initial state is the upright state. We can reset the pole to vertical after each failure. So when this pole fall down, then we need to reset. Okay. Here we consider two features. One is the angle, which is theta. The angle, the pole to this standing vertical line. Okay. Angular velocity, which is the theta point. Theta point, then provided by this moving car. Okay. In some sense, actually, this angle and angular velocity has a relationship. They actually has some mutual affecting the process. So for example, if the theta is small, means that so this pole is kind of try to stabilize itself to maintain to this to be upright, right? Then if at this moment, so this vertical angular velocity is high, it means that we are trying hard to maintain this pole to be this upright position. If this theta is large, which means like this pole is about to fall down, so it will fail to maintain this standing position. Then, if at this moment, if the theta point is high, actually it's not good for because it will accelerate its failure. It's accelerate its drop down, right? So this is an example about how those features may interact each other. So previously, if we just consider the simple linear combination, linear function like x, so here, yeah, a linear function. So if we use a linear function of the weight vector, so we just use a weight vector with a linear function. The xi is a feature, each xi. So if we just use this way, then actually there's no interaction among different features, okay? Each xi is independent space. Okay, yeah. So this is the problem which we are talking here. Now we are moving to this. Then actually there are several methods or basis function can be used for this feature design. The first one we are talking about is a polynomial basis feature. Polynomial basis features. So since some reinforcement learning problems use numbers, so to do the interpolation and the regression task, for example, the pole balancing task. So we are using those sensing information, those data are numbers. So we are trying to to do regression tasks like position and velocity. So we can use a polynomial to represent those numbers. For example, we can use two numbers x1, s2 to represent a state s. In this case, xs equals s1, s2. So remember here, originally the state is s. Now we are using this subscript 1 numbers to represent the features of the states. Okay. So as I mentioned, we mentioned in the previous the example, there's no interaction between these two features, right? Between these two features, S1, S2, they just update their weight by themselves. So also, if both numbers are 0, then state also 0 means that actually they cannot represent where for some states value. Now we can use another way to represent these features. We use a 4-dimensional feature vector, which can be S1, S2, S1 times S2. So in this case, we have use 1, it will represent the original states, the original state value. Then S1, S2 will be some two features like sensor reading or some position. Yeah. For example, here, a pole balancing task, it can be the position, can be the velocity of the car, right? So the S1, S2. Then we can also introduce the interaction between two features, S1 times S2, if they have this product relation, okay? So now we can generalize the polynomial basis. So suppose that each state S corresponding to k numbers. So actually we are using k features. This k number means k features to represent one state, okay? So S1 to Sk. So each feature is a real number. For this k-dimensional state space, so we are extending this original state to a k-dimensional state space, right? Each order n polynomial basis feature xi can be written as, so this we use this the feature xi. So xi is one feature to represent this s, and equals the product of the different combination of this k-dimensional states, these k-dimensional state spaces. So Si. So where each Cij is an integer in a set of 0 to n, which represent the order n. So what kind of order you want to reach, you want to design for your features. So this xi is one feature. Xi is one feature, okay? If you have a multiple feature, x1, x2, x3, and each of them will have a different like combination of this s from I to k. So for example, once you define the s1 to sk, then for a particular feature, it should be some product of the state spaces, okay? So these features make up the order n polynomial basis for dimension k, containing n plus 1 to the power k different features. An example, for example, if we design this axis, it's a vector, right? Then we can have 1, s1, s2, s1 times s2, s1 squared, s2 squared, s1, s2 squared. So actually, if you look at the last one, we will know what is the order. Here, the order means that the maximum, here in this case, the maximum, the power, which is 2 plus 2, which is 4. So this xs is the order 4 polynomial base features, the functions for these state spaces or feature spaces. In practice, because since this equation represent the general form of the polynomial basis, so in practice we just select subsets of the features. So in this case, actually this case it covers the possibility of n equals 4. For example, for this case, we just need to select like some of them, not all of them, subset of these features, not all of them, considering the exponential growing of the features with k. So if you use a large number of these k-dimensional state space with the k is very large, then your feature space, let's say this feature vector, will be very large. But actually, some of the features are not necessary or not useful for us. So this is the generalized polynomial basis. So just recall so xs is a feature. If you go back to maybe I should put the linear function here, okay? So xs, so you remember the linear function, then this w transpose times xs. Xs is a linear function. So if we just use previously we just used xs itself, I mean, yeah, it can be just some simple like feature, the state itself, okay? Now we are extending this xs to polynomial basis. So it can have a multiple polynomial basis function, okay? So to represent. So previously wi times xis. Now it's kind of a wi will times different. In this case, we are times so one of them, okay, one of the feature here. So this is how we use this linear basis function, okay, polynomial basis function here. So go back, continue. So this is about the polynomial basis. Then we can also, there's another type called Fourier basis function. The Fourier basis function is from the Fourier series. So you can check this Fourier, you can search for the Fourier series. So it's an expansion of a periodic function fx in terms of infinite sum of sines and cosines. Okay, as you can see here, fx can be expanded. So fx should be a periodic function. You should need to have a periods, right? Different period repeat pattern. It can be represented, expanded to in terms of infinite cosine and sine terms, and with the sum, them together. Okay. Then the AK and BK are coefficients, so which considers the orthogonality relationship of sines and cosine. So it means that some component will be used, some component will not be used. So if you are interested in this Fourier series, you can check the related information. But in our case, but you need to understand the key part of this Fourier series is. So it means that actually for a periodic function, we can use cosine, either cosine or sine to represent any function. Okay. So in this case, we can just use in our case, we just use cosine features to represent as a basis function, to represent as the k-dimensional state spaces for the feature. So the reason we use the cosine feature instead of the sine is that cosine feature is a half-even function, tend to be easier to approximate than the half-odd function, which is sine. So because sine function will cross the origin, right? If the origin, then it's possible that at the origin, the function is discontinued, not continuous function, right? Then it causes the indifferentiable problem. We cannot use the SGD. So then one-dimensional. So as an example, we consider, like, for example, we have a one-dimensional order n Fourier cosine basis. So it has n plus 1 features. For example, here, one-dimensional order n. So xi equals cosine I pi s. So this is a very simplified form of the Fourier basis function, the one-dimensional order n. So s belongs to 0 to 1. So this is a range. So it's become 0 to 1. So we limit the range of s. So then if we put the different I, 1, 2, 3, 4, we got the 4 different frequency, the cosine graphs, right? So they have different frequency. So this, if you put 1, 2, 3, 4, it will adjust the frequency of these cosine graphs. So now we just get these 4, like, say, features. Okay. Now we are generalizing this Fourier basis. So suppose that each state S corresponds to a vector of k numbers, similar to the previous definition, right? This k number, which means so each Si belongs to force between 0 to 1. Okay, this is not set, it's a between. So Si shall be the number between 0 to 1. It's a continuous space, okay? And the inclusive, so from starting point and ending point. Then the I's feature in the order n Fourier cosine basis can then be written. We use this term to represent a particular feature based on the Fourier basis. So we use the cosine pi s transpose times ci. So ci. So actually here we use this c is the vector. Ci equals multiple the order, actually multiple the state spaces, right? To represent to match these state spaces S1 to Sk. So with Cji belongs to, so now it becomes a set. This is order n depends on the order and the maximum order it can have. So actually this order also defines the frequency, right? So you put to here, it would define the frequency. How the higher order, I mean higher frequency. Then for j equals 1 to k, j is just, follows this state spaces, and I equals 1 to n plus 1 with power to the power k. Okay. So this vector ci, this vector ci affects the frequency of that dimension. Then with the order, different order. So from 0 to, for example, you have a 5, then this cosine, a particular component of this cosine will have a higher frequency. Then lower, if it's 0 or 1, it will have a lower frequency. So in practice, we use partial components of this Fourier basis function to represent the states. So for example, an example of Fourier basis is if we consider k equals 2, here k equals 2, then S only has 2 these state spaces. A particular state is represented by the 2 state spaces, 2 states, let's say feature. Then each where each ci is ci1, c1i, c2i transpose. So now we can calculate this one feature, x1s equals cosine is pi s1 s2. So based on this here, right, we write the pi is a number, so we just put here the s1 s2, then c1 1 c2 1 is transposed. So so then this is vector times this column, this row times this column, then we can rewrite. So this x1 feature actually has these 2 components, cosine pi s1 c11, cosine pi s2 c21. So si, so remember si, the s1 s2 actually falls between 0 to 1, is a continuous range, and ci depends on the order. Okay, the higher order, then the higher frequency, lower order, lower frequency. So for example, if we use n equals 5, means the order 5 Fourier basis. Now we can draw some figure to show what it looks like. Here is a selected 6 2-dimensional Fourier cosine features. If you use 0, 1, so which is here, C11, C21, which is 0, 1, it will, because if it's 0, means actually it's just 1, right? And if this is the 1 is the basic, if you look at here, it will just the basic, the lower frequency cosine graph. So put them together, actually you can draw this figure. So 1, so the x-axis is S1, the y-axis is x2. So we have this the different patterns here. Because 0, 1, actually the S1 actually didn't change, right? Doesn't change. Similarly to here, then this S2 doesn't change. And if we consider like 0, 5, so x1 doesn't change, but so S2 changes, follows the with order 5 and 5, the higher frequency. Yeah. So I mean, we can draw multiple these kind of features, the graphs, to show how we can use it. So this is a Fourier basis. How we can use it. Similarly, so this is x1. If we go back to, maybe I should put the linear combination here. So we would the W1 times x1s. Okay, so will be used as the basis, the feature space of xi in the vector in the previous we was seeing. Okay. So there are some remarks on this Fourier basis. So it has trouble with discontinuity. So it need to be the continuous function. Okay, if there's some discontinuity, then there's a like a singularity point. It just cannot be mathematically cannot be calculated. If the dimension of the state space is small enough, we can use all of them, all of the feature with a selected n. So as shown here, if it's n equals 5, actually you can see that this has a 5 with the states is 2. Actually, we can have 2 times 5, 10. Right, we can have 10, right? 10 the combinations. So we can have these 10 graphs. So then we can, if this is small, we can use all of them. But if it's too large, we can select a subset of these features, similar to the previous setting in the polynomial. We don't, when we define the feature space, we don't need to use all of them. We can select subset of them. One advantage of Fourier basis is that it's easy to select features by setting Ci vectors for possible interaction, limiting the values in Cj vectors for filtering out high frequency components, noise. So means that if you if you know you have a knowledge for some particular setting or problem, so you can especially use that part as the component, okay, to introduce this interaction. If you know that you have this pre-knowledge about this setting, that some of those high frequency the components are not useful, you can just limit the value, make it to become 0. So we will not consider those parts. Another point is that Fourier basis represent the global property of states. Nonce make it difficult to represent local properties. So it's kind of consider the, it represents the when you define the states, so it represents the global information of the state instead of some local information, okay? If we compare, as I mentioned, if we use this MC method, gradient MC method to do the state estimation, similar to the example we have been using, the 1,000 state random walk, then if we run this gradient MC method with Fourier basis and polynomial basis with the order 5, 10, 20, if you run 30 runs, then we want to check this error, right? The value error. We can clearly see that, so there's 2 different settings. For the polynomial basis, actually the errors is worse than the Fourier basis. The Fourier basis shows a better performance compared to the polynomial basis. Coarse coding. Coarse coding. So sometimes, so we can use, if for example, for a particular problem, for example, you are dealing with images, many images. So you want to represent different status in the images, in an image. So that we can consider it a 2D space, right? So we can use, one of the methods is that we use some circles with the binary features to represent the state. In this case, for example, here, consider you have the like a 2D space, then you want to use multiple circles to represent one state. For example, here, with this state S, in this case, we use 3 circles to represent this S, which is similar to the state aggregation. But state aggregation case is that we kind of divided them into multiple groups. So each state will only be activated by one group, right? But in this case, actually, the one state will be represented by multiple groups. In this case, 3 groups, 3 circles, okay? If the state is inside a circle, then the feature has the value 1, otherwise 0. If we move the state to another point, S prime, in this case, These states will be represented only two circles. This one and the other one, two groups. So these two circles will be set to value 1. So this kind of method is called coarse coding. It's like, use a generalized group to represent some particular states, right? Generalization in coarse coding. So actually, when we design these kind of groups or circles for representing states, sometimes we can use the small circles. Sometimes we can use the larger circles. Sometimes we can even like squeeze some circles, make it become irregular, become elongated circle. So usually, if we use the small circle, actually each circle will cover less states, right? If some states will fall into here, some states. So means that the generalization for this setting will be narrow. Here we use narrow or we use small. If you use a larger circle, so means that each circle will cover more states, right? So for a particular state, it can be activated or can be represented by multiple these circles or groups. So we call it broader generalization. A symmetric generalization is that asymmetric means that now, so because we kind of squeezed the circles, and in this direction, they cover less cases, less states. But in this direction, they cover more cases, right? So then actually they have a asymmetric coverage for the cases, right? So now the problem is that what are those impacts or effects on the approximation, this state value approximation, where the narrow generation give the finer approximation, the better, a very accurate, more accurate approximation, or this broader generation, where this broader generation will give a coarse approximation. Then in this case, what will it represent? Where it gives you a finer approximation in a particular direction because we are elongated the circles. So yeah, so for a particular direction, it may have a finer approximation. Actually, it's not true. The approximation depends more on the total number of features. Total number of features means that the number of circles here. Actually, for this, even though we have these small circles, actually we have a lot of features. We have larger circles, then we may have less circles, less features. Similarly, so if you look at the one example is that we have this this function. Then we want to use this coarse coding to approximate this function. Then the number of example is that how many features, how many circles we are using. Actually, if you look at here, so also the narrow feature, medium feature, broader feature means that the size of the circle. If the small size of circle, medium size of circle, larger size of circle means the broader feature. Then if you round it enough, actually if the number of the features is small, actually all of them will not give a good approximation, right? But if you increase the number of features, eventually actually most of them they give the similar approximation of the target, right? This is a proof that the important thing is that the number of circles instead of the shape or the size of the circle, okay? This is coarse coding. Then tire coding. Tire coding is a form of coarse coding for multiple dimensional continuous spaces. Previously, we considered these 2D spaces, right? 2D space. Now we are considering these multi-dimensional continuous spaces. So we can features are grouped into partitions of state spaces. When we say, so we will look at the example later. So first we receive some concepts here. Each partition is called a tiling. Each element of the partition is called the tires. So features are grouped into partitions of the state spaces. So the state aggregation we learned before, right? Is a special case of one tiling. Okay, if you just have one partition, then it becomes a state aggregation. We look at here, the left-hand side. So, for example, you have this continuous 2D space. If you use this the partition, right? One partition. So in each partition, they have these multiple cells. Okay. So each cell is called a tile. Then we can, for a particular state, for example, this point in this state space can be represented by one particular cell. Then most of the time we use multiple tiles to represent states. In this case, we use 4 tiles, tiling 4 tilings, tiling 1, 2, 3, 4, to represent these target spaces, right? Target these continuous space, 2D spaces. Then, so each tile, for example, for these states here. So these states, so okay, each cell we first I need to introduce this. This cell represent one feature. Okay, so one tiling has this 4 times 4, 16 features. Then we use 4. Then in this case we use 4 tilings to represent this space. Then so for a particular the state point, it will be represented by 4 tiles. So each one is called tires, also a feature, means that this one particular state will be represented 4 tires in these 4 tilings. Okay. Totally, we have this 4 times 4 times 4, 64 component tires or 64 features to represent each small the state in the target space, right? So similarly, if we run this 1000 state random walk example we look at before, if you run it enough, the state aggregation and the tire coding, so obviously we see that the tire coding has a better performance. Okay. Oops. So yeah, so let's take a break and we can continue from the radial basis function. Okay.